recording. Okay, what is this inverse function all about? So remember that we were talking about the functions. These are the machines, the assignments, the rules, which have an input. You can plug in inputs and it spits out an output which depends on that function, on that input and the function, definitely. Now, we want to see if we can create a machine which does exactly the opposite thing, meaning that it reverses what the machine F has done. So takes the one input output of F and spits out the input which gave us that output. In other words, mathematically, or fancy way of writing that, if inverse of is a function which is defined this way, if inverse of y is equal to x, if and only if f of x is equal to y. So it reverses the process that the function f does. Right away at the beginning, then the question comes up, does f inverse, don't read this one as f to the power -1. You have to note that this is not reciprocal like the algebraic inverse. It's not 1 over the formula of f of x. This is a machinery which reverses what the f has done. So f inverse, does it always exist? The question is, well, flat out no, not always. For f inverse to exist, we need to make sure that f has a nice property, and it's called 1-to-1. What is 1-to-1? It means that different, so if you have different inputs, they will give you different outputs. In other words, one output is not going to be received or obtained by two different inputs. Or equivalently, if x1 is not equal to, oops, this should be x2. If you plug in two different inputs, then their corresponding outputs must be different. And this way, basically, we guarantee that the reversing process is well-defined process. For every output of the function f, we have a unique input, which f inverse will take it as an output of that value. Well, to check one-to-oneness of a function, you can either do this or do that property. These are the same thing, and you can use either of them. For example, I can show you that every non-constant linear function, well, by non-constant we mean ax. First of all, by linear we mean ax plus b, where a is not equal to 0, that's non-constant. Every linear function, non-constant linear function, is 1-to-1. I just want to show you how the properties works here. So how this definition basically work here. Well, you see, I will start with this one. I take two different inputs. Since a is not equal to 0, when you multiply a to x1 and you multiply a to x2, these guys are going to be two different values. And then I can add b to these expressions. Since the original values were different, then if I add the constant thing to these ones, these will be different. As a result, I have shown that f at x1, the output of x1 is going to be different number than the output of x2. So we have shown here that if you have two different inputs, their outputs is going to be different. So that means that f is 1-to-1. Well, non-examples or counterexamples is I will say either one you like. Well, f of x equal to x squared is not 1-to-1. Why is that so? Because if I start, well, I will use this other definition for that just to show you that how the other definition can be used. So if I start with kind of the first version, but let me just go. So I take one output of this guy. So this is one output for some x. So y is positive. Then I can put this one as f of something. Then I want to try to see what would be the input which will give you the y. Okay, so it means that I want to solve it for x and see what are the inputs which gives you that y. So for that, I will take the square root of both sides. I'm solving for x. I want to try, I'm interested in finding what are the inputs that gave me that y. So, well, this is nice. Root of x squared. What is root of x squared? Can anyone tell me what is that?
Plus or minus x.
It's x. What else?
The absolute value of x.
Absolute value of x. This is very important. It's very deeply related to what we are doing. Square root of x squared is absolute value of x. It's not x. And that means that, well, absolute value of x must be equal to root y. But something, absolute value of something is a number. So that means that that something is either plus or minus that value. So we solved it for x and we saw that there are two inputs, while plus root y and minus root y, which give you the same output. So this means that x squared is not 1-to-1. Well, there are other ways of checking one-to-oneness. One of them is using the graph. And there is something called horizontal test, horizontal line test. Let me see if it seems that I have a question there. Yes, Willow, yes, please.
Would you mind explaining the previous example that you did? Because I still don't understand why that example would be like a one-to-one function, I guess.
Well, I'm trying to see that if I have two different inputs, their corresponding outputs are going to be different. That's the definition of one-to-one, isn't it?
Yes.
So what is the output for x1? It's ax1 plus b. What is the output for x2? Ax2 plus b. And in this process, I showed that if to start with, I start with two different values of input, the corresponding outputs are going to be different. ax1 plus b is going to be different than ax2 plus b.
Okay, so if only I guess if you had f of x, or yeah, f of x1 is equal to f of x like 1 again, would that not be a one-to-one function, or what would be like
Yes, if there were a chance that we get the same value, same outputs for different inputs, then that wouldn't be a one-to-one.
Okay, makes sense. Thank you.
Oh, you're welcome. Okay, checking one-to-oneness using graph. This is simpler way if you know the graph. Well, how does that work? So every f is one-to-one if and only if every horizontal line intercept with the graph of f at most once. Well, for example, the example that we have here, f of x equal to x squared. Check the graph. This is the graph. This is the famous parabola guy. And then if you draw horizontal lines here, there's no points, intersection point. So it's good. But if you go to the positive side, oh, there are more than one. So this is why this is not one-to-one. Or similarly, f of x equal to absolute value of x. Yes, do you remember the graph of this guy? This is the V-shaped graph. And as you see, if I draw a horizontal line up there, it's going to intercept the graph more than once. And that's why this is not one-to-one. Milo, do you have question again, or you forgot to lower your hand?
Sorry, I forgot to lower my hand.
Okay. Any questions, any comments? Okay, so now if you know something is one-to-one, how are you going to find the inverse of that function? I'll do this through an example. Remember what was the definition of the inverse? It is a process, a function, which reverses what the original function has done. So it means that if we start with one output, we want to see what was the input of that function which gave us this. In other words, we are interested in finding what is the x which satisfies this equation. We are interested in finding the input which gave us that output. Okay, so what we do, we'll try to solve it for x. Y is fixed. We try to solve it for x. I multiply both sides by x minus 1. I get this, and then I expand. I get this. Remember, I'm interested in finding input, meaning that I'm interested in finding x. Yes, so I'm trying to solve it for x. Bring all the x's one sides. And then factor out the x. And then you find that, oh, this is the x. So for that output of f, this is the input we are trying to find. In other words, f inverse, the reversing machine, takes anything that you give it to, it is available for it. You take it, and then it will do 1 plus that guy, and that guy minus 4, and that is the input of f, which gave us this output box there. And well, we are trying to find f inverse. So f inverse is doing the same thing. Remember this placeholder thing. Now I can put anything I like. Instead of x, you can put, instead of y that we found here, you can put x. The key point is that now we know what is the reverse machine doing. It turns every output here into the input of the original function. This is always true. When you're trying to find f inverse, you must go y equal to that function and then solve it for x, for the input. You're interested in finding what is the input, which gives you that output. Any questions, any comments here? One important fact about the inverse, or maybe application of inverse, is that, well, remember that I was telling always that finding range of function is not easy act to do, but if f is invertible, where it's 1-to-1, then range of the function f is the same thing as domain of f inverse. Recall that finding domain is always easier than finding range. So by this thing, if you know what is the f inverse, you're turning the range of the function, finding range of function, to finding domain of another function. And the similar things, or equivalently, there is another statement here that domain of f itself is going to be range of f inverse. So the f inverse changes the domain to range and so on. So for example, here I can use now use this fact to find the range of function that we worked with in the previous example, 4x plus 1x minus. There might be different ways of doing this, but since we have the inverse of this function, we know that range of this function f, which we are interested in, is going to be the same thing. This is the fact that I'm using. Same thing as domain of its inverse. But its inverse, look, it's a rational function. And for the rational function, we know that the domain is everything, but what makes the denominator non-zero? Oh, sorry, but makes it 0. So it will be all x's in R for which x minus 4 is not equal to 0. And this is equivalent of saying that all x's in R for which x is not equal to 4. If you want to write it in terms of interval notation, this is the notation that you will get for the range. So that's other ways. Well, sometimes finding f inverse is not easy itself, but that's how we do. If you know what is the f inverse of a function, you have to try. You can find domain of that, and that's going to give us the range of the original function. Any questions? Any comments? Yes, Kiara, please.
0, does that say x minus 4 plus 0 in the?
No, not equal to 0.
Oh,
the denominator cannot be 0.
Okay, that makes more sense. Thank you.
Well, I will leave this other example for you to do it yourself. It's very similar to what we started. Just as a hint, I will leave it a hint here. So you start with this thing, you solve it for first you will be able to solve for x cubed. So you will find that x cubed is equal to something times y plus another thing, something times y plus, I don't know, star, something like that. And then the very last step is that you do take the third root and that would be what you will do. So you just y equal to function of x, solve it for x, and that's in this case will be something like that. So I'll leave it for you to complete it yourself. And I will pass to the next topic there, which is the graph of F inverse. Yeah, any questions, any comments before I move down? Okay. Well, remember for the graph of a function, what is the graph? What does form the graph of a function? So let's say every point, the first component is the input of that. The second component is the output of the function when you plug in the first component as input. Now, the F inverse does the other way around. It takes the first component, sorry, the output of the function, and spits out what was the first component that gave you that output. In other words, this is F inverse of y. Well, this means that the points which form the graph of F inverse are basically the points of graph of F, but then you flip them. You turn X and Y. This is reversing the process, yes? And now, but reversing process has a nice geometrical meaning. So switching XY coordinate has a nice geometrical transformation. It's you find the reflection of the graph with respect to line y equal to x. That's what flips the xy coordinate. So this will be something like that. So if this guy here is F, this guy here is going to be the graph of F inverse. So the process going from F to F inverse is the transformation is reflection about y equal to x, line y equal to x. A very quick question here. I will answer this one. So you have a function f, it's 1-to-1. Now we are trying to find the graph of the function whose graph is obtained from the graph of the function f by doing the following operation. So we start with function f, and then we have reflection about y equal to x. We know that that happens if we interchange x and y. In other words, we turn f to f inverse. Whatever the function is here, you find its inverse. In this case, we already know this is f inverse x. The next step, the next transformation is horizontal shift 2 units to the left. So this can be obtained by turning x to x plus 2. Yeah, and that will give me, so whatever was here, you take the x, you turn it to x plus 2. So this is the function that we are looking for, f inverse of x plus 2. I have an example for you to find. This is a nice example. It's a little bit trickier, but this is for you to do it yourself. You just follow the steps. Just remember the reflection is whatever function you have here, you find its inverse. That will give you everything there. So you take, to start with whatever is that, you find the inverse of it. Any questions, any comments here? I will post these questions on these notes on our page, yes, but if you like, you can. Okay, then it's time to go work on very important functions that the instructors of this course and this course designers love the most. These are trigonometric functions, and you want to find the inverse of trigonometric functions. To start with, inverse of sine. Well, this is a very important function. I want to see what is the input of an output of y. So I want to reverse this thing. But right away, I noticed that, sine is not 1-to-1. Sine is not 1-to-1. First of all, why it's not 1-to-1? Just look at the graph of sine function. Sine function is periodic function. So it just repeats itself infinitely many times on the real line. So any horizontal line between -1 and 1 will intercept with the graph of this function infinitely many. So that is why this guy is not 1-to-1. Well, then we gave up. We cannot do this. We don't want to because it's not 1-to-1. That's not right. When a function is important to you and you want to find its inverse, you can consider that function, in this case sine, on a smaller domain on which the function is 1-to-1. I will call it 1-to-1 domain. In this case, there are different conventions. The most, almost 99% of the time, the most important one, the most repeated one is the one you go from -pi/2 to pi/2. So we restrict our function to the domain -pi/2 to pi/2. And then, while here it is 1-to-1, it is 1-to-1. So I can define sine inverse of a number there. This is y if and only if y is equal to sine of x. So in other words, it's going the backward. It looks for an angle whose sine is given. So here x must be between -1 and 1, and here y must be in the 1-to-1 domain, the convention that we fix here. In other words, I can write this guy. This is domain of sine inverse is from -1 to 1. Range of sine inverse is the 1-to-1 domain of sine, which is -pi/2 to pi/2. What about the graph? Oh, I know how to do the graph. This is this guy here. Don't like that guy like that. So this is the guy here, and then the reflection with respect to this, something like this guy. And this will go from -pi/2 to -pi. That's the graph. Sometimes people like to write sine inverse, the inverse of function. It's not 1 over sine, it's the inverse of function as arc sine. That's the same word. Well, then one can go more and do more thing for cosine. We can also define cosine inverse of x, which is basically finding what is the angle whose cosine is x. And in that case, the one-to-one domain, this is very important, one-to-one domain of cosine is, look at the graph of cosine, it goes from, it's like that, and this is pi, so the domain, that standard domain that we will take in this course is going to be from 0 to sorry, I made a mistake here. This must be, am I doing right? No, this is, there's a mistake I'm doing here. This is why this is, again, I'm doing the same thing. I got so excited. I should write this one like that. And here, y is between 0 and pi. The one-to-one domain for cosine is that. For tan, you have the same story. And you're trying to find this tan, and that is, again, not one-to-one unless you fix a domain. In this case, the domain is from negative pi over 2 to pi over 2 not included. Well, x can be anything here. That's a different one. And then you just need to check the notes and the videos. We have all these things set up there, and you have to be able to find these ones. Okay. Okay, let's just evaluate some of these values. Sine inverse of negative root 3 over 2. Okay, this is interesting one. So I'm looking for a theta whose sine is negative root 3 over 2. But I have to make sure that this theta is in the one-to-one domain of sine. And in this case, well, what is the angle whose sine is root 3 over 2? I know that sine of pi over 3 is root 3 over 2. We know this. This is a special angle, yes? I also know that sine is an odd, it's an odd function. So it means that when you plug in negative, multiply the input by negative, the negative will be multiplied to the outcome. So from these two, you can conclude that, oh, sine of negative pi over 3 is negative root 3 over 2. We found the theta. That is the theta that we were looking for. These are almost the same story, so I will leave this one for you. Now, as I said, the important thing is that you need to know the one-to-one domain other than some special angle values. For example, let's do this other one, cosine inverse of 1 over 2. So if this is theta, this is an angle whose cosine is half, and we have to make sure that we understand the domain. One-to-one domain of cosine is from 0 to pi. So what is an angle from 0 to pi whose cosine is 1 over 2? This is one of the special angles. You should know this one from the table that we had. Cosine of actually pi over 3 is half. So that is in the interval. We are good to go. And this will be pi over 3. Similar thing, you can do it here. Say secant inverse must be equal to 2. So I'm looking for a theta whose cosine, whose secant is equal to 2. What is the domain for secant? This is very important. The domain for secant, you have to know these ones. And I believe in one videos, I have been doing that video for another book. The convention was different. But in this case, the convention in our case is 0 to pi. And we have to make sure that theta is not pi over 2. And well, if you do this one, then we are interested in 1 over cosine theta equals to 2. That's the definition of secant. So that means that cosine theta is 1 over 2. That's very nice because you already found then theta in that interval is pi over 3. So this guy is pi over 3. Well, these were the special angle cases, the ones that you can work a little bit around and you can find the value of inverse trig function. In other words, you know the trig ratios of these angles. Now the point is that what if I have more general cases? For more general cases, for example, someone can ask you what the sine inverse of say 0.35 or 0.3. Oh, I don't know that. We need calculator for this. So questions like this are off our chart because this is not, we are not supposed to use the calculator. But someone can ask you a question like this. Sine inverse of sine of an angle. So we are looking for a theta such that sine of theta, you see, this is the definition. Sine of this guy is equal to sine of 7 pi over 5. And we are interested specifically in theta being between minus pi over 2, that's the 1-to-1 domain of sine. One may say that, maybe let me ask you this one. Can anyone give me an angle whose sine is equal to sine of 7 pi over 5? We don't know value of sine of 7 pi over 5. It's not a special angle. For that, we need calculator. But there is a key point here that we can find an angle like that. Well, if you have cases like this, remember identities like this will be always helpful, that sine of theta plus 2 pi is always equal to sine theta. But specifically what we are interested in here is that sine of theta pi minus theta is equal to sine of theta. How you can prove this one? This is just the sum formula. Use the sum formula for sine alpha plus beta. And that will give you sine pi cosine theta minus cosine pi sine theta. You will see that that will give you that property. What I'm trying to say is that, okay, turning this number to a number, an angle which is in this interval, sometimes needs some work to be done. So for example, sine of 7 pi over 4, 5 is equal to sine of pi minus 7 pi over 5. Based on this property. And this is nothing but minus, well, that's minus 2 pi over 5. So I have two different values of angle which give you the same sign. They have the same trig function sine value. But this guy here is an angle between negative pi over 2 and pi over 2. So this is my theta. So the theta here is sine, negative pi over. You see, in general, there is a fact that I want to remind you here, remark, is that when you have F inverse, you apply it on F, that will give you X back. Because it's reversing what F has done. They cancel each other. Or the other way around is also true. In the case of sine and cosine, or sine inverse function, you have to be very, very careful here. This is not always equal to X. This is not true. Sine inverse of sine X is not X unless X is in the interval, one-to-one interval of sine. And sine of sine inverse of X, this is X if you know that X is in between negative 1 and 1. Those are the domains that you have to know, and in that case this works. This story will go up, only will work for the domains of these guys. So the given domain that will work. Okay. That's one of the examples that we have done already. You see the sine inverse of sine of 7 pi over 5 is not 7 pi over 5. It's negative 2 pi over 5. It's a different thing.
Professor?
How about this one? Is there any questions, any comments?
Could we do an example where the x isn't in the interval?
If X is not in the interval negative 1 and 1, this doesn't make sense. You see, we cannot plug in sine inverse of 10. It doesn't make sense. That's why when sometimes that I write this thing, assuming that this will work for possible values of X, I won't write X's between negative 1 and 1. It really doesn't make sense to write sine inverse of 2, 10.
Yeah, I was asking for an example specifically, but
it doesn't make sense. It's not defined. That's not a correct question. Okay. How about this guy here? Okay, so this is a little bit different, but as I said, if you have cosine of cosine inverse of an X, which is between 1 and 1, this is going to be X. Well, if you know that this is well defined and the number is given there. So that's why in this case, this is going to be 1/3. You don't need to do any work there. Okay. For this example, I want really to do this example before we go. Sine of cosine inverse of an angle, 2 times of that. For questions like this, you have to start by applying here, in this case, double angle. Double angle for sine is sine of 2 alpha is 2 sine alpha cosine alpha. So this is 2 sine of cosine inverse of 0.35 times cosine of cosine inverse of 0.3. Well, we already did an example like this. Cosine of cosine inverse of a number between 0 and 1 is going to be that number. And there is 2 up there. So now I have to find what is sine of cosine inverse of 0.35. You see, cosine inverse of 0.35 is an angle. And by this, we know that cosine of theta is equal to 0.35. This angle is going to be on the interval. Since this is positive and theta is in that angle, theta will be in 0 to pi over 2. Okay, so then I can draw a triangle for this actually. If this is 1, this is theta, this is cosine of theta, which is 0.35. And then here will be sine of theta. Yes, so sine of theta, just to use Pythagorean theorem, it's going to be 1 squared minus 0.35 squared. Is it going to be plus or minus based on the fact that cosine is positive and theta is in that interval? This is going to be only positive. So we have found the value for sine of cosine inverse of 0.35, and that is root 1 minus 0.35 squared. This is 0.7 root 1 minus 0.35. Yes, Joshua.
For the sine inverse of sine 7 pi over 5,
Yes,
the 7 pi over 5 is not in between negative pi over 2 and pi over 2, right?
that's correct. Yes.
So like, and then for the answer, all you did was you found the reference angle of that.
Yes, exactly. So that's the best way of putting it. But for reference angle, if you mean an angle which is between negative pi over 2 and pi over 2.
Mhm.
Yes. So I found an angle which is in that interval and has the same sine value.
I see. Okay, so these kind of questions, even if the x inside the bracket is not in between negative pi over 2 and pi over 2, it could still be solved. Like,
Yes,
right.
exactly. Because sine of any angle, any number you put there, it makes sense.
Oh,
You see?
EB.
Yeah. Who was so excited hearing that? Yes, Josh.
Yeah, that makes sense. Thanks.
Okay, perfect. Before I go, I just wanted to add this point. I have some examples for you, but before I go, I just want to make sure that you see there is new restrictions for the domains now. So before, domains were, we got domains based on 2 things. Denominator cannot be 0. Yes. Under the even roots must be non-negative. Now with sine inverse, cosine inverse, all these things, you get new restrictions. sine inverse domain of, if you have sine inverse of something, that something must be between -1 and 1. If you have cosine inverse, that's the same thing. For tan inverse, we don't have any restriction. If you have secant inverse, there's a restriction for this kind of thing. So in this case, I will just write it as a hint. Now you know that domain of this function must be all x's in R, for which 3x minus 1, the input of sine inverse, is between -1 and 1. And then you solve it for that and then find the domain. So just know from this section on, we are going to have new restrictions for domain. If there is sine inverse there, you will see later log will come in. So those new restrictions must be applied as well as we go on in this course. And I have another DIY for you. So make sure that you do those examples and you make sure that you understand all of this. I will stop recording here. That was all I had to say for today.